looking at just some basic, like reminding ourselves about some geometry, vocabulary, as well as starting to look a little bit at like angles. And we started looking at radians. Today we're going to look at a little bit more vocab, and then just kind of start trying to convert back in between degrees and radians. But as a reminder, a degree measure is a measurement an angle given by of 1 degree, which is 1/360th of a circle. A lot of words. You don't have to write all that down. Basically, the 1/360th of a circle is probably the more important part. Remember, we have 360 degrees in a circle. Arbitrary basically just means someone made it up. They came up with like, this is how much a degree is going to be, and they went from there. So I think we talked a little bit about yesterday that the problem with degrees is that it's harder to get really, really small with degree measurements, which means that they aren't always the most accurate. We also have this like degree symbol or unit that is attached to it. So that can be bad depending on if we're not wanting like extra units in it. So that's why yesterday we went through our little activity to remind ourselves about, or learn about, if you haven't heard before, about a degree measure of radians. Okay? So remember that our radians are equal to, a radian is the arc length equal to the radius of a circle. Remember, an arc length is just like an outer portion of a circle. So this would be an arc length, and this length and this length are equal to one another. However, remember that it's really difficult to take a straight measurement and turn it into a curved measurement, which is why we used the string yesterday to help us do that. Which is why I also remember in our book that we read, when we try and relate things that are straight to things that are curved, we end up with our special number, which is pi. Okay? And so that is where, through our little investigation, we came up with the fact that 2 pi is equivalent to 360 degrees for 1 full rotation of a circle. And we talked about a little bit that that is our unit, right? Okay, so remember that unit conversions just mean like fractions, right? I'm going to have to multiply by some fractions to reduce stuff. However, we want to multiply by the reduced rate of that. So can 2 pi and 360 be reduced by the same thing? Or is there a number that goes into both of them? Yeah, what is it? 2. Alright, so if I divide 2 pi by 2, what do we get? 5. If I divide 360 by 2, we just go ahead and use the reduced rate. Okay? So what that means is that if we want to convert from degrees to radians, okay, we're going to multiply by pi over 180 degrees. So hopefully we've done some conversion rates in like our science classes, as well as maybe like pre-algebra or algebra 1 when we convert from like inches to feet, right? So whatever we're trying to make go away, so in this case, the first one, trying to get degrees to go away means whatever I multiply by, that thing, in this case degrees, has to be in the bottom. Same thing if it's the other way. If I'm trying to get rid of radians, I need radians to be in the bottom. So when we're doing these conversions, okay, we want to just focus on the fraction first, okay? Because remember that pi is not a very nice Greek number. It's 3.14 forevermore. So when we're doing some reducing, we're just going to look at the number stuff first, and then we'll add the pi at the end. So we don't want to type stuff into our calculator with the pi, because then you'll get a really ugly number, right? So we're going to do one together, and then you're going to do the one that is on your handout that I gave you. Alright, so I have up here 135 degrees. If I am wanting to convert 135 degrees to radians, okay, what has to be on the bottom of my fraction in order to make degrees go away? 180 degrees, right? Because the whole reason, or the whole thing that we're doing is we're trying to get our degrees to go away. So if I have one on top and one on bottom, now they reduce out, okay? But I also have to have my pi relationship on top. And so this is the part where I said we just really want to focus on our fraction. So notice that this is technically over 1. Yes. So we have a 135 on top and a 180 on bottom. So we want to try and reduce that first and then just add a pi. So is there something that goes into both 135 and 180? Okay. What's 135 divided by 5?
27.
And 180 divided by 5?
36.
Okay. Is there anything else that goes into both 27 and 36?
9.
Okay. So instead of reducing by 5, what is 5 times 9?
45.
45. Okay. So instead of like, you could either reduce it twice, okay, because again, we want the most reduced possible. So like if you reduce by a number and then you notice that it can still be reduced, then we just reduce again, okay? Or we can reduce both of these by 45. How many times does 45 go into 135? 3. How many times does 45 go into 180? 4. Great. So now, what's my fraction part? I have what on top? 3 and a 4 on bottom. Okay? So we just write our 3/4, and then we tend to put the pi. So you put 3 pi over 2. You can also put 3/4 pi. Either one is fine. Basically, we're just going to add that pi to the end. Are we all okay with that? Now, on your second one, I want you to do the ones on your paper. So 225. extravagance, not always the case, just happened to be the case for these two. So if we reduce those, we should end up with what?
5/4.
Yes. Now, on this last one, as we continue on, we will remind ourselves that normally when we measure angles, we are going to go counterclockwise. I'm going to look at that in a second. But what that does mean is that if we need to go the opposite direction, we can just throw a negative on there. And that just means that we're rotating in the opposite direction. So that's really all that negative means. But that does mean that when we reduce it, we should also end up with a negative radian. So what goes into both 270 and 180? 90. How many times does 90 go into 270? 3. And it goes into 180 twice. But we do need to make sure that we carry across that negative. So we get negative 3 pi over 2. Now, the more that we deal with radians, the better that we'll get at them. Okay, so if you haven't used them in any of your previous classes, it's going to take a little bit of practice, just like anything else that's new. Okay, we are working on conversions. However, I would warn you again. Anytime that I give you a problem in radians, don't just convert it to degrees because you like those more, and then convert it back to radians at the end, because that's going to take a lot more time at the end of the day. So once we get better at radians, we should be able to do stuff with radians fairly quickly. Okay. Now there will be some questions where it's necessary that we have one or the other, and so that's why we're working on it. But don't use this as a crutch and just always convert to degrees, because that's what you see the most. Okay. But on that note, we still can convert things from radians to degrees if we need to. So basically, we are just going to flip the fraction that we multiply by now. In order, once we do that, we are able to get our pi's to reduce this time. And so then again, we're just reducing a fraction. So I have 180 degrees over 2, which is also what? How many times does 2 go into 180? 90. Again, we have a negative. Okay, so I just need to carry my negative across. So I get negative 90 degrees. Alright. I want you to do the second one from your handout. So 5 pi over 9. Okay. Yes, that's right. Alright, now on my example, we have our RAD, rad, which stands for radians, written out every single time. Okay, most of the time we don't write out RAD for radians, we just don't put anything. Remember, it's like a pure unit, so we just, if there is not a degree symbol, then we assume it is in radians, which means that when we have our units are in degrees, it's going to be really important that you put your degree symbol on there. So we have 5 pi over 9 times, again, 180 degrees over pi. Again, our pi is reduced. How many times can 9 go into 180? 20. So then we end up with 5 times 20, which gives us 100 degrees. Now, let's do this last one together. We do need to be careful. Okay, so notice that I have 2 times. So this is still in radians, so I still need my pi to be on the bottom. Yes? But do I have a pi on top to reduce with? No. So be careful, because we did have the rate, or the unit rate that 2 pi equals 360. But like technically 2 pi is approximately like 6 point stuff, right? And that equals, so 6 point something radians is equal to 360. I don't have 2 pi radians, I just have 2 radians here. Yes? Okay? So, in this case you wouldn't need a calculator, because you're just going to do 2 times 180, which gives you 360. And then you're going to need to divide that by pi. So you're just going to use your pi button in your calculator. And what do we get there?
114.59.
Okay. Which makes sense, because if we remember from yesterday, 1 radian on our little like plate, right, was like 55, 57-ish degrees, right? Somewhere in there, a little bit less than 60. So it makes sense then that if I had 2 of those, we'd be, a little bit more than 100, but less than like 120. Yes, or maybe? What questions do we have there? Our angle thing slowly coming back to us from geometry. All of the geometry words we haven't heard in a minute. Alright. We're going to talk a little bit about angles, so we'll get these last 2 definitions, and then we'll stop there for today, and we'll have a couple more examples that we'll do tomorrow. So, in general, remember that an angle is going to be the space between 2 rays connected at a common endpoint, which we also will call our vertex sometimes. Okay? So basically, remember, we talked about a couple of things. What's a line? Like, we use line to mean a lot of different things, but like the geometric-y idea of a line, what does that mean? Like, what's the difference between a line and a line segment? Yeah, in both directions, right? Lines go on forever, both directions. Versus line segments have endpoints. So technically, whenever we use the word line, just in everyday use, we are technically talking about a line segment, right? Because we don't actually mean something that goes on forever. So then, what is a ray?
It goes on forever in one direction.
Which is why it has a common endpoint. So I have 2 rays, right? So they both go on forever, but only on one side. And then the stuff in between them is what we would then call the angle. Now, this is an angle, okay? We could also say, like, over here is an angle, or over there is an angle, right? We can draw the angles however we want. But as we found out yesterday, some of us are better than others at using a protractor, right, to figure out what our angle measurements are. So depending on how it's drawn, it can be a little bit hard to know what that angle measure is. So we came up with just like this standard notation or standard position for angles, and it's much easier to figure out what an angle measurement is. Okay? So standard position is where the initial side is on the positive x-axis. The vertex, or basically that point that they connect at, is at the origin. And it rotates counterclockwise, which is kind of what we said earlier. In general, if we have a positive angle, we are rotating counterclockwise. So if we need to rotate clockwise, we have to throw a negative there. So again, that vertex there then is at the origin. My initial side is here. And then we rotate to however far we need to go, going counterclockwise. Now I know we don't like to go counterclockwise. I was really interested in why we rotate counterclockwise when we measure. It's like just like standard notation. But found out because you can blame the Greek mathematicians, because whenever they were starting to look at like angles and things like that, they didn't have clocks. They had sundials, right? And sundials move counterclockwise, right? The same way that the sun moves. So as the shadows were moving, right, it goes counterclockwise. And so that was kind of how they started discussing angles, and we've just kept that same notation, even though now our clocks move the opposite way, so like we're used to rotating that way in our head. So sometimes it does take a little bit of like work to be like, nope, gotta go the other way. But there you go. Any questions?